Hello everyone. Pharmaceutical organic chemistry is one of the important subjects that are being taught in Bachelor of Pharmacy. Myself Dr. Sandeep Kumar Bansal, Professor at Ramesh Institute of Vocational and Technical Education, is going to discuss the Pharmaceutical Organic Chemistry third, that is BP 401T. I am going to discuss the unit second of this subject. As far as unit second is concerned, it is clearly divided into 4 parts. Part 1 basically deal with the geometrical isomerism. In geometrical isomerism, we basically focus on nomenclature of geometrical isomerism, means how the various geometrical isomers are provided the name as per standard rules, like whether they are cis or trans, E or Z or syn or anti system. After assigning the nomenclature to geometrical isomers, we have to confirm, we have to identify that whether the given geometrical isomer possesses the desired configuration. So, in this section we basically discuss about the methods how to determine the configuration of the geometrical isomers. In this section we will discuss various physical and chemical methods. Second part deals with the conformational isomerism. Conformational isomerism arises due to rotation around single bond, and this topic will be discussed with reference to few molecules like ethane and butane and cyclohexanes. Part 3 will deal with the stereoisomerism in biphenyl compounds. If we talk about biphenyl compounds, they exhibit stereoisomerism, and this phenomena is also known as atropisomerism. Simultaneously, we will discuss about the required conditions for the optical activity, means how biphenyl compounds will exhibit optical activity. The conditions required for that we will discuss in this section. In part 4, we are going to discuss stereospecific and stereoselective reactions that comes under this section. So, let us start with the part 1 that deals with the nomenclature of the geometrical isomerism. So, before proceeding further, we should know what are the isomers. Isomers, first characteristic of isomers is this, that they possess same molecular formula. They possess same molecular formula, but they exist as a different compounds. So, the compounds with same molecular formula, but different identity, they are called isomers. Now, these isomers are classified basically in 2 types. One is called structural isomer and another is known as the stereoisomers. Structural isomers are also known as constitutional isomers. Now, what is the difference between structural isomers and the stereoisomers? Structural isomers are having different order of the attachment. They possess same molecular formula, but their order of attachment of different groups atoms is variable. But on the other hand, if we talk about stereoisomers, they are having again same molecular formula. Now, what is the difference? And identical order of attachment is there. So, this is the different point as compared to the structural isomers. Structural isomers have different order of attachment, but they are having the identical order of attachments of their various atoms groups within their molecule. But they differ in relative position of these atoms groups in space. So, that is the point that create a difference what are stereoisomers and what are the structural isomers. So, structural isomers are differentiate on the basis of connectivity, on the other hand stereoisomers are explained on the basis of their relative position in the space. Now, we can classify these isomers in broad sense. So, what are the isomers? Isomers are the compound with the same molecular formula. Now, there are two possibilities, they might have same connectivity or they might have the different connectivity. As I have told in previous slide that if they are possessing different connectivity, then we are calling them the constitutional isomers. But what happens if they possess the same connectivity? They are called stereoisomers. So, this portion we have covered till now means compounds with different connectivity are called constitutional isomers, compounds with same connectivity are called stereoisomers. Now, within stereoisomers again there are two possibilities that the stereoisomers can have the chiral center and they can't have the chiral center. So, now what does it mean? So, first of all let us go for some idea about the chiral center or chiral carbon. Any carbon that is associated with 4 different substituents. So, this type of carbon is called as chiral carbon. And if we talk about the chiral center, so to explain chiral center, one should have focus on the axis and the plane of symmetry. So, symmetry should not be there. If there is symmetry, the molecule will not be considered to possess the chiral center. Now, if we talk about again, if it is with chiral center or if it is without chiral center. So, if there is no chiral center, then we are calling them the stereomers. Means, so the stereomers are the stereoisomers without chiral center. So, they can be cis or trans, Ez. So, this type of isomers are called the stereomers. Now, what happens if they possess chiral center? Again there are two possibilities. First possibility that they can have one chiral center or they can have more than one chiral center. If they are having one chiral center, so this type of stereoisomers are called enantiomers and examples are DL, that is dextrolevo, RS, ricinososianister. So, this type of system is followed by the enantiomers. Now, what is the situation if they are having more than one chiral center? Again the molecule can be chiral or molecule can be achiral. Again two situations are there. If molecule is achiral, then meso compounds results. So, meso compounds are optically inactive compound due to internal compensation and the best example is mesotartaric acid. Now, if we look upon the another possibility that they are having with chiral center, now they can exist with mirror image or without mirror image. If they are existing without mirror image, again they will be considered as the stereomers. And we can look upon by taking the example of glucose or citric acid, tartaric acid. So, there are so many examples using them we can explain the phenomena of diastereomers. If they are available with the mirror image, then this type of stereoisomers are called enantiomers. Now, what happens? So, this we can see stereoisomers we are classifying in diastereomers and mesocompound, enantiomers, diastereomers, again enantiomers, depending on the presence, absence of the chiral center, or more than one chiral center, or more than less than one chiral center, or one chiral center, whatever is the case is there. Now, if we go for a rotation around a single bond, this type of rotation is called conformation, and isomers are called conformational isomers, and the phenomena is called atropisomers. If we restrict the rotation, the phenomena is called atropisomers. So, what are atropisomers? With the restricted conformational isomers, they are exhibiting the phenomena of the conformational atropisomerism. Now, let us come to the main point, how geometric isomers arise. So, geometrical isomers is one form of the stereoisomers, as we have seen earlier, and these isomers occur when there is restricted rotation somewhere in the molecule. This is a very important point, students. So, keep on focusing on restricted rotation somewhere in the molecule. Now, what does this restricted rotation means? So, what happens in a molecule where there is unrestricted rotation? There are two terminologies, two terms are there, restricted rotation and unrestricted rotation. And where we are talking about the rotation? We are talking about the rotation in between the carbon-carbon. So, carbon bonds, in other words, where the carbon-carbon bonds are all single. Okay. So, to explain it, let us have an example of 1,2-dichloroethane. This molecule is represented here. Let us assume it as a and it as a E. Here you can see that chlorine is represented by the green. So, this is chlorine. In the structure A, it can be easily seen that both the chlorine atoms are opposite to each other, but in this structure they are on the same side. Can they be different compound? No, both of them are the same. These two models are representing exactly the same molecule. But how we can say this? That these molecules are same? Because if we want to convert A to B, it can be easily done just by twisting. And if we are able to do this, then the molecules cannot be isomers. So, this is called unrestricted rotation. If unrestricted rotation is present in any molecule, we cannot consider it as an example of the geometrical isomer. Now, let us see what is the condition required then. Now, to explore it further, let us draw these two models with the help of a line diagram. Here you can see that chlorine, in these two diagrams, the chlorine atoms are on the same side, and here chlorine atoms are present transverse to each other. So, free rotation about the single bond. So, what does it mean? That both the molecules are same, both the structure what we have drawn, both are the same. So, these two structures are representing the same molecule, means there is no possibility of the geometrical isomerism, means it is a perfect example of unrestricted rotation. So, one thing it is very clear that unrestricted rotation can never result in the form of geometrical isomers. Now, let us try to restrict the rotation. Now, we are having example 1 2 dichloroethene. What we have did? Simply we have converted this C single bond C into C double bond C. These two molecules are not the same. The carbon double bond and would not rotate, and so you would have to take the models to pieces. How? What does it mean? If I want to change the position of this chlorine atom, I have to plug it out and I have to place it again here. Means I have to break the model to convert the structure A into B. And in previous example, it was not required. That was done beautifully just by rotating the structure. So, if I am not able to convert one structure into another just by simply by rotating, that means I have restricted the rotation, and this is called restricted rotation. So, my dear students, I hope you must have clear that what does unrestricted rotation and what does it mean the restricted rotation. Means if you convert one structure into another just by twisting, means it is following unrestricted rotation, and if one need to break the structure or pieces into pieces to convert one form into another, then it is known as unrestricted rotation, and the later one is known as the restricted rotation. So, this is the one video you can see, just watch this video. In this video, the structure that is rotating is first structure is example of the free rotation, and second example is the restricted rotation. So, you can clearly see that first example that you have seen was the example of unrestricted rotation. These two examples are of the restricted rotation. Now, what happens if we are restricting the rotation? What are changes taking place? So, the answer is the presence of this pi bond. If we look upon the energy of this pi bond, it is 284 kilojoule per mole. Now, if you want to convert structure A into B, as we have seen earlier, C double bond C, if the chlorine is there like present here, I want to change the position of chlorine like this. So, to convert this structure into that second one, I need to overcome this energy barrier. We have to break the bond, and the minimum energy required is 284 kilojoule per mole. And my dear students, at room temperature, significant number of effective collisions are very less, they are extremely unlikely, they do not take place. So, the possibility of such interconversion is negligible. So, the presence of pi bond and the energy required to break this bond is the basic concern that is hindering the conversion of a structure A into B. Means restriction of rotation creating this energy barrier, and due to presence of this energy barrier, we are not able to convert one structure into another structure just by rotation. So, my dear students, there would be hindered rotation around C double bond C, and thus both the structures should have independent existence. This is the reason that both the structures have independent existence. And how do we can prove this independent existence? This independent existence can be proved with the example of certain physical constant like boiling point, melting point, and the dipole moment. And such isomers are called geometric isomer, and these geometric isomers are also known as the pi diastereomers, because they differ in the geometry of the group of double bond, and phenomena is known as the geometrical isomers. So, these what we are calling these type of isomers that are resulting due to unrestricted rotation, they are called geometric isomers, or parallelly we are calling them pi diastereomers, and the phenomena is called geometrical isomerism. How to recognize the possibility of geometrical isomerism? Means what condition is required? Let us see this, if we look upon this molecule, it bears 3 substituent of similar, 3 similar substituent and 4 substituent is differ. So, can it result in geometrical isomer? Here in this case again you are having 3 similar substituents and fourth one is the differ. In later case, substituents are 2 substituents are similar and 2 substituents are different. So, the condition, next condition that is required apart from the presence of a double bond, there must be 2 different groups on left hand carbon and 2 different groups on the right hand one. So, at least different carbons must be present at both the carbons, this carbon, if we are talking this carbon and this carbon. So, both carbons are possessing different substituents and they can be similar with respect to each other or they can be different from respect to each other. Now, what happens? See, this is carbon 1, this is one carbon, carbon number 2. So, it is possessing 2 different carbons, it is possessing 2 different substituents, and this example shows that it is possessing all the 4 substituents that are not matching with each other, means all the 4 substituents are different. So, which will show geometrical isomerism or which will not show geometrical isomerism, it has to be decided. So, what we have to conclude right now, so to get geometric isomers, we must have restricted rotation. Generally, it is achieved with the presence of carbon carbon double bond and 2 different groups on the left hand end of the bond and 2 different groups on the right hand end. It does not matter whether the left hand groups are the same as the right hand end one or not. This is condition number 1, this is the condition number 2, means presence of a double bond and the 2 different substituents at left hand carbon and right hand carbon is required to be resulted in the geometrical isomers. Now, there is one more example that geometrical isomerism can also exist also in the cyclic compounds apart from this olefinic compounds. So, this is example of the cyclohexane. Now, if I choose these 2 carbons, and I am replacing 2 hydrogens with the bromine. So, can this result in geometrical isomers? Let us see, we can answer using this diagram. Now, these 2 bromines can have 2 different orientations. They can be above the plane, above the ring, they can lie above the ring or they can lie below the ring. So, this is the example of transform because one atom is above the ring and one atom is below the ring. So, cyclic compounds can also exhibit geometrical isomerism if they are possessing 2 different substituents. There are few more examples representing geometrical isomerism cyclo compound, that 1,3-dimethyl cyclobutane, 1,4,6-trimethyl cyclopentadiene, dimethyl cyclohexane, 3,5-divinyl cyclopentene. So, we must have this type of structure to exhibit geometrical isomerism. Now, condition is that C or D can be same or cannot be same, and similarly A or B can be same or cannot be same. So, this type of condition is required. So, these 2 structures means these 2 atoms should not be same, but A or C can be same or A or C cannot be same. Similarly, B or D, they can be same or they cannot be same. So, to exhibit geometrical isomerism, the compound must have these two conditions. So, thank you students. In next lecture, we will discuss about the nomenclature of geometrical isomerism. I hope you must have understand what I have tried to told you. Thank you very much.